Hello everyone, this is again Rico de la Peña, and this is a lecture on earthquake ground motion, specifically on the seismic response spectra for buildings, as based on the National Structural Code of the Philippines 2010 and 2015. Now, let's first talk about earthquake response spectra. This pertains to actually three different ground motions. So you have your peak ground acceleration, or the acceleration value that you typically get from the Fukushima and Tanaka equation, or for more modern methods, you can also use the PHIVOX probabilistic PGA maps. You also have your spectral acceleration, which and your spectral velocity. Now, it's more common to use the PGA in the spectral acceleration and the structural design. Spectral velocity is more often used in large structures like bridges, long bridges, right? And we won't be covering that for this lecture. All right, now, what we use here in the Philippines, unfortunately, is the NSCP 2015. Why I'm saying unfortunately, I will be discussing that later on. And this method allows for the calculation of PGA and the spectral acceleration at the resonant period. Now, resonant period is important because if the resonant period of the structure, like the building, and the vibration, period of vibration of the ground due to an earthquake, is if they match or once they match, this will result in resonance shaking. And it will result in a structure that will be accelerating faster and faster with every swing. So I have here a boss model video just to demonstrate how resonance works.
Of the different building models, this is my favorite. This
Alright, so
model
you can see
uses
here a
a
video
block of wood.
showing
In this case, they've got wheels
buildings
on
of
to make it easy
different
to
heights
move
that
back and forth to
correspond to
simulate
different
earthquake
periods.
vibrations.
Generally, the
And
shorter
these are
the
dowel
building
sticks of
is,
different lengths with blocks of wood on top. So we've got
the,
tall
the
building
smaller the
representation
height, the shorter
down
the
to short
period.
building. And I like if there's a group of people going
So you can
remotely,
just
but
skip his
often
introduction
it
here.
seems
It's a lengthy
vibrating the.
introduction.
Oh my goodness!
He starts at a
The
high
short
frequency
building moves the most.
shaking. So high frequency shaking or short period shaking will resonate
Okay,
with
well,
the
now you know what the answer is.
shorter
You get one more
structures which
guess.
have
So now a lot of people change their guess and say, well, I think maybe the short one will move the most.
short periods.
So now I make another earthquake. Say, well, here's another earthquake.
Now he shakes it at a lower frequency or a more slower
Oh,
motion,
lo and behold, it's a tall one now that's
and you can see
vibrating the
the
most.
tallest building
So at this point, I think
resonating
it's
with
good to
that
have
kind of shaking.
a question, an issue that for kids to think about for a second. Okay, now what's going on? There must be some trick to this. What is he doing differently between the short building moving the most and the tall building moving the most? And so then I explained that, well, it actually has to do with frequency of each of these buildings. The res- and you can see the short building moves back and forth very quickly when you just pull it and let it go. Tall building moves very slowly. And these move with intermediate frequencies. So if the ground motion is the same as the resonant period, resonant frequency of one of these buildings, the amplitude of the building motion will build larger and larger. So if I move the ground very rapidly back and forth, I'm giving a resonant frequency near this one. You can see the amplitude there gets very
Alright,
large.
so you're seeing a high frequency
And if I go
shaking
very slowly,
and a low frequency shaking
the taller building moves most. And you can also go to intermediate frequencies
and an intermediate frequency shaking
for this one
and a slightly smaller frequency shaking.
or for the blue.
Right, so I hope that explains to you how resonance works. So it's like an identifier for the building, that depends on the build, mostly depends on the building height and the uh, construction materials used. And of course, it also depends on the side of the ground. This will depend on the softness of the soils and other effects like basin effects and so on. All right, so yeah, seismic site classes or the period of the ground shaking will depend on the seismic site class, and this is best obtained through the seismic survey that will give you a VS30 or the shear wave velocity of the upper 30 meters of the ground. And we do this commonly in DPWH. What we do is we use a MASW survey or a multi-channel analysis of surface waves that can give you a good approximate of the shear waves of your site. Now, what also influences the response, of course, of your ground is first the size of the earthquake. If you will remember in the earlier lectures, a big earthquake is an earthquake that either spans a large fault or an earthquake that spans a small fault but outputs a large amount of energy. All right, so magnitude alone of an earthquake is not really enough to determine the intensity of shaking. All right, now, so another important stuff to determine the intensity of shaking during an earthquake is, of course, the type of the fault and the depth of the fault. Of course, the more shallow, the more destructive they are, and you get a lot of destructive earthquakes with your reverse or thrust faults compared to any other type of faulting. Now, NSCP as a method for determining ground response accounts for a range of earthquake sizes and distances, and this will be only constrained by the size of the largest earthquake that you specify. So essentially, NSCP has a range of motions, and you basically just set the upper boundary by depending on the largest earthquake that you can find near your site. And then the method aggregates the ranges of acceleration values per structural period. And you will see that later on the spectral curve that we will be constructing. Now, this is just an overview of how we can construct a seismic response spectra for buildings. Now, remember for buildings, there's a different method for. We're just tackling here the method for buildings. There's also a separate method for calculating the seismic response spectra of bridges, but we won't be discussing that anymore because it's really in the realm of specialized engineering. It's really a problem of the bridge engineers. In buildings, these typically involve small projects where it's common for the geologist, geotechnical engineer, and the structural engineer to have more or less overlapping uh, scopes of work, which can get really weird and awkward at many times. Anyway, the steps are as follows. First, you determine the seismic zone from the NSCP figure map. And the TLDR of this is if you're not in Palawan, your seismic zone, it's either are you in Palawan or you're not in Palawan. And you will see that later on. And then the next step is to determine the nearest fault to the site from the FIVOX map. And then determine or estimate the magnitude of earthquake that can be generated by the said fault. And then we go and obtain the NSCP seismic parameters from the NSCP table. So this is more or less quite easy to do. And then the next step is to obtain the seismic soil profile type. So this is sort of a classification system that tries to categorize how your soil will behave during an earthquake. And generally, the more clayey your soils, the softer your soils, the more horrible they are. Although the worst type of soils that you can encounter are of course your liquefiable soils. They are typically categorized as special problematic soils in a seismic design. So your liquefiable soils, your collapsible soils, your soils that are prone to consolidation, they are your special consideration soils. And they actually need a specialized analysis. But I don't commonly see it here in the Philippines for some reason, although it's specified clearly in the NSCP. So anyway, uh, we then proceed to again getting some NSCP values and then obtaining some ordinates that we'll be using to plot the seismic response spectra curve. So I won't be lingering in this slide. Let's move to the seismic zone factor. Alright, so this is what I'm talking about. It's either your site is in Palawan or in Sulu, or it's not. If your site is in Palawan, you're in zone 2. If it's not, you're in zone 4. So our site is in Zambales, so it's in zone 4. So zone 4, and the Z value is zero point 0.4. Right, so that's our Z value. This actually corresponds to the raw peak ground acceleration. All right. So this is the uncorrected peak ground acceleration. We typically correct the peak ground acceleration by factoring in the type of soil that is underlying the site. If you have clay or soft soils, the PGA will increase. If you have bedrock, the PGA will decrease. Now let's look at the seismic source type. So we are in Zambales, and you can check Google Earth and then open the active faults and trenches map of PHIVOX. Okay, in their website, they actually have a KMZ file that you can open in Google Earth. And from there, it's really convenient. You can just see the faults that are near your project site. So in this case, in this Zambales project, the nearest fault is, I think this is the East Zambales fault, which based on the historical earthquakes. All right, so I also have here a plot of the historical earthquakes in the Philippines that are based on the USGS catalog and the study of Bautista and Oike. All right, so the Bautista and Oike study is really cool. What they did is they just compiled all the accounts of earthquakes from the Spanish friars, and then they just tried to convert the descriptions of the earthquake damages into magnitudes. And so we actually have a 400 year long record of earthquake in the Philippines. And that is really rather unusual. Okay. All right. Anyway, so our estimate on the magnitude of the fault is 6. All right. So if you look at the NSCP table, table 28.4 on the seismic source types. So if you will look, 6 will fall under type C, or faults that are capable of earthquakes of less than 6.5 magnitude. So we have a seismic source of type C. Now we move on to the other NSCP NSCP parameters, And we can see here from the Google Earth that East Zambales fault is 21 kilometers away from the site. So 21.6 kilometers. So we just select in these columns. So this falls under the greater than or equal to 10 kilometers. And then earlier we determined that the seismic source type is type C. So type C and this column will give you a n sub a value of, or the near source factor Na of 1.0. Now for the near source factor NV, again we look at the distance. So it falls under the greater than or equal to 15 kilometers. So 21.6 kilometers is greater than or equal to 15 kilometers. And again, the seismic source type is type C, and we get a value of 1.0. Now, uh, we also have to classify the site for its seismic soil type, which is most accurately determined by doing a seismic survey to get the VS30. Or if you're more or less working on a smaller budget project, you can use the drilling logs and the SPT and the RQD. So there are methods to convert SPT and values in rock quality designation into VS30 values. There's a lot of methods described in the literature. You can just search them in Google Scholar, or you can use the methods described in this manual. But this manual is not distributed to the public, so you can just search. Can't remember the author, but you can just search SPTN to VS30 and RQD, and you will definitely get a different methods that you can choose from. Now, let's say that the survey in the site we did a seismic survey and we found out that the seismic shear velocity in the upper 30 meters is 411 meters per second. All right, so there are many ways to convert VS30 into seismic site class, but 411 meters per second squared correspond to seismic site class A. So we can just do a quick Google search, NEHRP seismic site class. Yeah, and you can see here, you can basically see this figure from NEHRP. So you can see here seismic site classes, VS30 velocities, and SPTN values. So, all right, sorry. So VS30, that's corresponding to site to 411 is actually SC. All right, so sorry, there should be a correction here. So let's just change the VS30 to 1600 for the sake of accuracy. So let's say the VS30 of the site is 1600 meters per second. That will correspond to a seismic site class of class A. All right. So we can just actually add this to the presentation. Right. Right now, so seismic site class A correspond. All right. So getting the seismic coefficient C sub A. So you just have to know the seismic zone, which is this column. So zone 4, and then the seismic site class is A. and you will get a value of 0.32 times n sub a. Now, if you will remember from the earlier slides, our near source factor n sub a is equal to 1.0. All right, so Ca is equal to 3 point is to equal to 0.32 times Na, and that is 0.32 times 1.0, and we get a Ca of 0.32 meters per second squared. And then for the seismic coefficient Cv, this again boils down to the seismic zone, which is zone 4, and the soil profile type, which is type A, and you get a value of 0.32 NV. And again, if you remember, CV is equal to 0.32 times NV. And earlier, we found out that NV is equal to 1.0 here. So 0.32 times 1.0, you get 0.32 meters per second. All right. So this value is actually your peak ground acceleration, and this value is your peak ground velocity. They coincidentally somehow matched up, but they're not always the same. Now let's proceed to the construction of the seismic spectral response curve. And of course, we need first these ordinates. So T sub S is equal to CV divided by 2.5 Ca, and that will give you 0.32 divided by 0.32 divided by 0.2, 2.5, and you will get point and you will get 0.40 seconds. And then T naught is just zero point 0.2 times TS. So zero point 0.2 times zero point 0.4, you get 0.08 seconds. Now, we can do that in a spreadsheet, all right? So I actually made a customized spreadsheet to construct a seismic spectral response curve. All right, so let's fill it one by one. I mean, sorry. So let's just look at the figure first, just to give you an overview of what ordinates are we talking about. So this curve is made up of one, two, three, four elements. So first is the first point that we plot, which is the 0, comma Ca. Okay, so the first point that we plot in order to construct the seismic response spectra is the 0 second structural period and the peak ground acceleration. So this point corresponds to the peak ground acceleration. Okay, so the vibration of the earthquake at 0 period is your peak ground acceleration. So that is your first point. 0 Ca, that's equal to, so your Ca is just equal to 0.32. All right. Now note that this y-axis is actually different. This is expressed in meters per second squared. All right. This one is expressed in G. So we can also convert that by multiplying it by 0.981. You get 3.392, and that is this point, approximately this point. And then the second point that we plot is T naught and paired with 2.5 Ca. So T naught is basically just 0.008 seconds, And then the CA is 2.5 CA is this one, zero point 0.8, but you have to express it in meters per second squared. So that is equal to 7.85, sorry, 7.885. Right, so approximately that value. And then the T sub S, comma 2.5 CA is this one. So our T sub S is zero point 0.4 seconds, so this corresponds here, corresponds to this one. Now see, we have constructed the three lines of the response spectra. Now what remains to do is to just calculate this line, this curve. So we do that by taking values of t and CV divided by t at different times. So the start of the curve is at zero point 0.4 seconds. So we start at this point. So structural period, so that's your t. Structural period is your t, and then your corresponding spectral acceleration is equal to CV divided by t. All right. So all right. So this is our start. These are our starting points. So it's the curve starts from here and drops down, and this curve is just defined by this equation. So our first entry is just we can just add increments of 0.25 or 0.15. It doesn't matter. So you can even try increments of zero point 0.1, right? And just drop it down. That's weird. So zero point 0.1. This is weird. Six. Okay, so we go from point. So let's just focus on this structural period. So we just our aim here is to just fill up uh, to generate a list of a list of values of structural periods from zero point 0.4 up to 5 seconds. All right, so let's go from zero point 0.4, then zero point 0.5. Then you can just add a random increment, like let's say zero point 0.1, and just drag it down until you reach 5. So this is a lot. Let's try a smaller value, like just zero point 0.2. Zero point 0.2, and drag it down until you, sorry, that's not right. So zero point 0.4, zero point 0.6, zero point 0.8, then drag it down, then delete it at 5 seconds. So so we have completed the structure periods from point 1 from point 4 until 5 seconds. Now we just have to calculate the spectral acceleration in g. And from the formula, spectral acceleration is just CV divided by the current structural period. So at this point, at this uh, period of point 6, the structural, the spectral acceleration is just equal to CV, which is CV, it's in the top value here, CV divided by the time, and you get 0.53. All right. Now we can drop down this formula, but first we have to anchor. We just anchor the cell reference into the CV so that we can just keep our reference to the CV because it's constant. So we just drag that down. All right. So let's just check a random formula. So the spectral acceleration is just CV, which is this value divided by the structural period. All right, so that makes sense. Now we can just adjust this plot to accommodate the whole series. So we have the values of the spectral acceleration z in g, but this plot is shown in units of meters per second squared. So we just have to merely convert it by multiplying the value by 9.815. So you can just drag that down and make sure that the plot is referencing to the values properly, right? All right, so that's how it should look like. All right, so that is your seismic response spectra curve. Now, we d- in order to interpret that, we have to determine first the actual structural period of the building. But for a quick approximation, we can quickly look at the three important values here. First is the peak ground acceleration. Of course, structures are always designed for this value. And then you also have your short period spectral acceleration. This is normally significant in low-rise buildings. Okay, short period spectral acceleration typically corresponds to structural period of zero point 0.2 seconds. Right, as you can see here, or around between zero point zero 0.08 to zero point zero 0.04. Okay, and you're getting an acceleration of around 8 meters per second squared. Now, for long period spectral acceleration, this is typically more important in high-rise structures and bridges, and that corresponds to a structural period of 1. Okay, but of course, you want to interpret this more precisely. What we have to do is to calculate the natural period or the structural period of our structure. And for that, we have to specify an example structure. Our example here is a concrete structure that is 3 stories high. So that's a typical residential apartment structure. And the formula to calculate the structural period T sub n is equal to coefficient C sub T times the height of the building raised to the power of 3/4. So our structure is concrete. We can just look at this table from NSCP. And concrete building has a C sub T of 0.0731. And a 3-story building has a height of approximately 10 meters. So plugging in those values into the equation, 0.0731 times 10 and raising the height to to the power of 3/4, you get a period of 0.41 seconds. So that is the structural period of a three-story building that is concrete in terms of materials. Now we go back to our seismic response spectra curve, which we generated for the site, which is located in Zambales. And 0.41 seconds will approximately correspond to this point in the seismic response spectra. And this has a value of spectral acceleration of around 7.5 meters per second squared, right? So whoever is the structural engineer should be aware of that parameter, right? Designing for that is already none of our business. It's already the job of the structural engineer at this point. All right, now I mentioned earlier that NSCP is an unfortunate method, and this is my reason. NSCP 2010 and 2015 still use the Universal Building Code of 1997 for obtaining the response spectra calculation. So the method that we discussed earlier is still based on a method dating back to 1997 from UBC. And UBC is a US method. To be specific, it is based on Californian earthquakes and Californian landmass. So what you have in California, your most famous is your San Andreas fault, which is a transform fault. Alright, so most of the earthquakes in California are transform faults, your strike slip faults, which don't really generate a lot of, I mean, per magnitude they have. Their shaking is not as intense as here in the Philippines, where you get reverse faults, shallow faults, trenches, which are more energetic per magnitude, per a given magnitude. All right, and this is actually being addressed partly by FIVOX. Right, this is FIVOX is currently doing a study. They're trying to measure the seismic velocities of different sites in the Philippines, and they're prioritizing the metropolitan areas and the mega cities like Iloilo, Davao, Metro Cebu. And they're also, of course, incorporating the earthquake database in the Philippines there. So they're now trying to get or trying to formulate a method, or rather a map, that would describe the seismic response spectra in the Philippines that are based on actual measurements of the sites, not based on a continental setting. And of course, the responses are also based on actual earthquakes that have happened in the Philippines, and not those based on Californian earthquakes. So I hope that partly explains why NSCP is kind of a uh, rather old method to use, but it's still being used in practice, right? And unfortunately, and that's why I'm still teaching it here. There are no really the alternatives to the UBC uh, are still not being implemented. All right, so I hope you learned something from this lecture. All right, so if you're involved in a geotechnical investigation, geological geotechnical investigation, you now have an idea how to construct a seismic response spectra for a given site and a given structure. All right, so thanks for listening.